Hello everyone, I am Yan He from the University of Oklahoma. The paper I'm going to present is MotionCompass, Pinpoint Wireless Camera via Motion-Activated Traffic. This is a joint work with Qiu Ye and my advisor Dr. Fang from the University of Oklahoma, and also Dr. Liu from University of South Florida. As we all know, growing awareness of safety and security has boosted the growth of security camera markets. In 2019, worldwide security camera shipments totaled 64.8 million. For 2020, the global market is expected to reach 33.89 billion. It is forecasted that the global wireless camera market increases at an annual growth rate of as high as 16.85% over 2017 to 2023. Wireless cameras are widely deployed in our daily life. In outdoor environments, they can be installed on a wall to monitor the front door. They can also be hidden under eaves, near common equipment, in a tree or birdhouse. Similarly, in indoor environments, a wireless camera can be embedded in everyday objects, such as clock, speaker, power outlet, smoke detector, or even a Wi-Fi router. Some wireless cameras are made visible as a deterrence measure. However, the visibility may mean more susceptible to damage or theft, and more likely to be the targets, as the burglars may think the camera indicates there are valuables. Also, an adversary may find blind spots to avoid them. Due to these reasons, people may hide their wireless cameras. On the other hand, the popularity of wireless cameras also brings privacy concerns associated with unauthorized video recording. For example, according to a survey of Airbnb guests, as high as 58% concerned about is there any hidden cameras in their room, and 11% said that they have discovered a hidden camera in their Airbnb. Detection of wireless cameras is drawing increasing attention. Let's review existing techniques. Basically, they can be divided into three categories: lens detection, physical search, and radio frequency scanning. The first two methods require to inspect every corner of the target area, and they are obviously cumbersome. For radio frequency scanning, it only works when the camera is actively transmitting. Meanwhile, existing radio frequency scanning work but can only detect the existence but cannot tell the camera's exact location. In many scenarios, however, detection is not sufficient on its own, and we regard that the wireless camera localization is important, and it is the problem that our work aims to solve. For example, by finding the physical camera, a victim whose privacy is violated can obtain the direct evidence. Usually, we cannot watch the camera for all time. To overcome this limitation, a great portion of wireless cameras equipped motion sensors. As the figure shows, the camera remains in standby mode until movement is detected, at which point the camera turns on and starts recording, and then upload the recording video to the cloud as well as send a notification to the owner. This figure more clearly shows the variation of the intercepted traffic. In standby mode, there is only a heartbeat signal of small size just for synchronization. Once the human activity is detected, an abnormal wireless traffic would be generated. When the activity ends, the camera reverts to standby mode. Our idea comes from this observation. When we artificially introduce motion at a spot, if we observe a corresponding high wireless traffic, we know this spot may be monitored by a camera, and we may determine the camera's possible error accordingly. Furthermore, if we customize the motion path, we can then narrow down until pinpointing the location of the camera. Our work includes three important phases. The first phase closely determines the wireless traffic associated with wireless cameras. The second phase aims to extract the MAC address of the camera. The last phase achieves the localization through manipulating the camera's traffic. The first phase is quite straightforward, and I'm going to introduce the last two phases in detail. A MAC address of a wireless device has 6 bytes. Normally, it is determined by the 16-on-chip manufacturer, and it has the following format. The first half is often fixed, called OUI, namely Organizational Unicode Identifier, indicating the manufacturer and the device type, and the second half is the device ID. We can thus build a table containing OUIs of all cameras on the market, and then use it to determine whether the monitored traffic belongs to a wireless camera or not. As shown in this figure, for each MAC address extracted from local traffic, if its OUI can be found in our OUI table, we can then determine that the MAC is for a camera. In this way, we can sort out the MAC address of an Amazon B-Link wireless camera for this example. Without loss of generality, we consider a camera deployed on a wall. Thus, the camera localization problem can be converted into computing the coordinate of the camera on the wall. In order to obtain the maximum horizontal breadth, the camera body is often mounted perpendicular to the wall, like the figure. The camera moves just up and down. This is the special case. In the general case, the camera can be swept in any direction, and it can be mounted at any angle to the wall. Here, we introduce how to localize the camera for the special case. We develop a two-step procedure to obtain the camera's coordinates. As shown in the figure, the user first moves parallel to the wall, from left to right, or in the opposite way. The walking path is called path 1. As soon as the user walks into the motion detection range, we record the starting point A, current time t sub 1. When the user steps out of the zone, we record the ending point B and the current time t sub 2. With the walking speed v, we can then calculate the distance of the line segment AB. We plot path 1 in the XZ plane now. Here, we can clearly see that the camera's x-coordinate, c sub x, equals half of the line segment AB, plus the x-coordinate of point A. Note that the point A's coordinate can be measured easily. Thus, c sub x can be obtained. In step 2, The user performs motion along path 2 to vertically get out of the motion detection range. Starting from the midpoint of the line segment AB at time t sub 3. When the user exactly steps out of the motion detection range, we record the ending point D and the current time t sub 4. Similarly, with the working speed and the time span, we can calculate the distance of the line segment MD. We plot path 2 in YZ plane. With the line segment MD, the point M's z-coordinate M sub z, and the angle DCC prime, we can then obtain the camera's y-coordinate C sub y by applying this equation. To deal with the general case, we also developed an improved two-step algorithm to obtain the coordinate of the camera. The user just needs to perform motion along one extra path. Please refer to our paper if you are interested in this algorithm. For the evaluation, we developed an Android app and tested it with 18 popular cameras in total. They can be divided in two groups, G1 and G2, based on the number of motion sensors the camera has. We perform experiments in both outdoor and indoor scenarios, and for each scenario, we choose 5 different locations to place the camera. To quantify the performance of MotionCompass, we use two metrics. First is the localization error, which is the distance between the estimated and true locations. The second metric is the localization time, which equals the amount of time spent on pinpointing the camera. This slide shows the performance across different locations in different environments. We have 3 observations. First, the camera localization error is always less than 9.2 cm. Meanwhile, the localization time is always below 178 seconds. Second, camera in second group show larger localization error and time in both environments. This is because a camera with 2 motion sensors has a larger motion detection zone. Last, outdoor scenario shows larger localization error and time, regardless of the group. The difference appears due to the fact that outdoor environments provides a wider space, and the user may spend longer time generating the simulating motion. Next, we verify that MotionCompass works for different cameras consistently. As shown in these 2 figures, outdoor and indoor localization error, we can see that a high localization accuracy can be always achieved. Specifically, for group 1, namely camera 1 to 15, the minimal localization error ranges from 1.0 to 2.3 cm. And for group 2, the range becomes 3.1 to 4.5 cm. In conclusion, we propose a practical solution to pinpoint a motion-activated wireless camera. Accordingly, we build a model to correlate manipulated motion with the corresponding wireless traffic. Also, we developed an Android app and successfully verified its effectiveness and efficiency with extensive experiments.